All right, here we go. Consider this function x maps to 2x plus 3. On the same axes, graph f and f inverse. Okay, so I need a graph. Bam. Okay, this is a line, has a y-intercept of 3 and a slope of 2. If you didn't recognize that, we could very easily make a table of values and graph it that way. But there's f of x. Now to graph its inverse function, I'm simply going to switch the ordered pairs. So for instance, this one is 0, 3. The inverse will have the point 3, 0 on it. This point, negative 3, negative 3. If I switch those points, negative 3, negative 3. This point, 1, 5. That means 5, 1 will be on my graph, my inverse. And I've got enough points now that I can make this graph. All I really need are 2. I like to get a couple more just to make sure I'm not making any huge mistakes. On a graph like this, where we're graphing more than one thing, it's really, really important that we graph this, or label our graph. So find f inverse using coordinate geometry and the gradient of f inverse from this graph. So slope, gradient would be 1/2. And then I'm going to use the slope formula, which is basically point slope form. Y minus any y minus, 1 over any x minus 5. All I'm doing is I'm using that point. I should be able to take any point in here, any other point for x, y, and get a slope of 1/2. So y minus 1 has to equal 1/2 times x minus 5. Y equals 1/2 x minus 5/2 plus 1. I'm adding 1 to both sides. And 1 is really the same thing as 2/2. Y equals 1/2 x minus 3/2. And that basically looks like where I'm crossing the y-axis. So that is using coordinate geometry to find the inverse. Now it says to use variable interchange. What we're doing here is we're using the fact that if y equals 2x plus 3, the inverse will simply interchange the two variables. X equals 2y plus 3. Now, to graph this, I want y by itself. So I'm going to subtract 3. Divide by 2. Y equals x minus 3 over 2. That's our inverse. And that's the same thing we got using the slope formula. Basically, the rule of thumb is to find an inverse algebraically, you take x and y, you switch them, and then you solve for y. Any function which has an inverse and whose graph is symmetric about the line y equals x is a self-inverse function. And we saw one of those in the previous section. F of x equals 1 over x is a self-inverse function. Its inverse is itself. And that's all we've got for inverses. Important thing to know is that inverses get us back to where we started. They get us back to just plain x. And what the last thing I want to do before we finish up, I want to verify that this has an inverse of this. So let me get this down on paper here. And then the inverse was 1/2 x minus 3/2. To verify that these two things are inverses, we have to do these function compositions. And we need to end up with x both ways, and we have to do both ways. So I'm going to start with f inverse. 1/2 times something minus 3/2. That something is 2x minus 3. So x minus 3/2, x plus 3/2, minus 3/2 is x. So the two functions have just undone each other. And then we take function f first, and we plug it into f inverse. I did this completely backwards. This one I took f and plugged it into f inverse. This one I want to take f and plug in f inverse. And again, we end up with x. And because both of them undo each other in both directions, these two are indeed inverses of each other.